So in the previous one we are talking about the address calculation in 2D array. So now in row major implementation, when we are implementation in row major implementation, we are implementing through row major. So address of a of I comma j, we need to find out the address of ith row and jth column address. So that is nothing but base address plus number of words per memory cell into I need to write I plus j, and if it is row major, then we need to multiply the row part with the number of columns. If there are m into n order of matrix, m is the number of rows, this is the number of rows, n is the number of columns. We have number of rows, n is the number of columns, and in row major we need to multiply the row part with the number of columns. And in column major, address of aij is equivalent to base address plus w I plus j. In this case the column part is multiplied with the number of rows, so it would be j into m. This would be j into m, because we will find out the column part multiplied with the number of rows. So let's take an example how we will solve the numerical. So suppose we have we need to find out the address of A12. We need to find out the address of a first row and second column element, and the implementation is row major. It is given to us, the implementation is in row major form, and the array A23, 2 rows and 3 columns, the array would be 10, 20, 30 and then 40, 50, 60. We have 10, 20, 30 and 40, 50, 60. We have this 2 rows and 3 columns. So in row major form, we need to find out address of A12. How we will calculate? Base address is 102. It is given to us. Because this is integer type of data element, we will consider w as equivalent to 2, because this is integer element. Now what is I is 1, what is j? 2. Now this is row major, so in row major we will multiply the row part with the number of columns, and how many columns we have? 3. So 1 into 3 plus 2, so the answer is 11. And if we calculate A12, address of A12 in column major, if we are considering column major, now we are considering column major. So if we are considering column major, so we will need to calculate 102 plus 2, 1 plus 2. In this case, in column major, we need to multiply the column part with the number of rows, and how many rows we have? 2. So this is equivalent to 102 plus 2, 5. This is also 112. This is also 112. So why the row major and column major address is similar? This is because the first row, this is 0th row, this is 0th row, this is first row, and second column, this is 0th column, first column, second column. So first row and second column element is the last element, and in row major as well as in column major, the address of first as well as address of last element is same, whether it is implemented through row major or whether it is implemented through column major. In that case, the address would be same. In any case where we have, the address would be similar. So let's suppose I'm taking a different tricky example of address calculation. Let's suppose we have a 25 cross 4 matrix score. We have a matrix 25 cross 4 matrix score, and the base address of score is equivalent to 200. It is given to us, and this matrix, particular matrix score, stores the score of 25 students in 4 matches. It stores 25 students score in 4 matches, right? So we can visualize it as like first, second, third, so on up to 25th student, first match, second match, third match and fourth match, right? So this is the scenario. We have 25 students and 4 matches, and the score is stored in this particular matrix. And if we want to find out the 12th student score in third test match, we need to find out 12th student score in third test match. We need to find out the 12th student score in third test match. How we will calculate? So in this case, in this particular example, we have taken the indexing from 1. However, in matrix, the indexing will always start from 0. So if we can, this particular scenario, we can visualize it as from 0 to 24 and from 0 to 3. This could be the scenario. This could be the scenario that we have 25 students and 4 matches, and it is stored with this. So we need to find out the 12th student score in third test match. That means it has been stored at 11th location and 11 cross 2, 11 multiply comma 2. The address would be in this particular scenario. We need to find out the score of 11 comma 2. So we can easily calculate score of 11 comma 2 is equivalent to base address, which is equivalent to 200 plus number of words per memory cell, that is equivalent to 2, I plus j, and it is implemented through row measure. So the row part would be number of columns, and the number of columns would be 4. Number of columns would be 4. This is 44 plus 2 into 4 plus 200, and that is equivalent to 384, and this will be the answer. So in this particular examples, we need to very alert in visualizing the things. We need to be very alert in visualizing the things. So because we are taking the indexing from zeros, that's why the formula is like this. Always we are taking indexing from 0. That's why the formula is this. If we have indexing from any other, like if we have indexing from 1, if we have indexing from 1 to something, so this I plus j is equivalent to I minus 1, j minus 1, and in row measure it will be multiplied by number of columns, and in column measure the column part would be multiplied by the number of rows. So this is row measure formula, and this is column measure formula when we are taking indexing from 0th, first location. And when we have some lower bound, and upper bound, then the formula will change. So how we will talk about this? So let's suppose we have, like, let's take an example and we will solve that example through some lower bound and upper bound. So we have an array A with lower bound of row is 4, upper bound of row is 7, lower bound of column is -1, and upper bound of column is 3. And it requires 2 bytes of storage space. It requires 2 bytes of storage space for each element. And it is stored in row measure. It is given to us that the array is stored in row measure form, and we need to find out the address of element at location 6, 2. So how we will calculate? Remember this, that when we are finding out the address of 6, 2, this is equivalent to base address. Base address is equivalent to 100. Number of words per memory cell, I minus में LB of row plus J. What is J? J is 2. 2 minus में LB of column. And because it is row measure, the row part would be multiplied by the number of columns. So now what is the number of columns? Number of columns would be what is number of rows? Number of rows is equal to M. M means upper bound of row minus upper bound of column, upper bound of row. upper bound of row minus lower bound of row plus 1. Upper bound of row is 7 minus 4 plus 1. That is equivalent to 4. So the number of rows would be 4. And how we will calculate the number of columns? Number of columns will be equivalent to 3 upper bound of column minus lower bound of column plus 1. This is the formula. Upper bound of column is 3 minus lower bound of column is minus 1 plus 1. That is equivalent to 5. So the number of column would be 5. So the address of A62 would be equivalent to 100 plus 2, 6 minus 4 multiplied by 5 plus 2 minus में 1. 2 minus में 1. That is equivalent to 100 plus 2, 10 plus 3, 13. That is equivalent to 126. So this is the address of A62. When we have some lower bound, we have some upper bound, then we have calculated the address like this. Next topic is time space trade-off. What is the meaning of time space trade-off? So time space trade-off is something like when I want less time complexity, I need to increase the space. When I want more time complexity, I need to reduce the space. So space and time complexity are inversely proportional to each other. Like I can say, I can have minimum time complexity when we increase the space. So that is called as time space trade-off. Just an example of linear search and binary search. Again, I am repeating what is time space trade-off. The time and space of an algorithm are two major measures of the efficiency of the algorithm. Sometimes the choice of data structure involves the time-space trade-off by increasing the amount of space. When we are increasing the amount of space for storing the data, one may reduce the time. One may reduce the time needed for processing the data. So the example of this is linear search and binary search. Linear search and binary search. In linear search, the time complexity is high because in linear search the time complexity is n, and in binary search the time complexity is log n, because in this we will check the middle element, then the array is subdivided into two halves, then we will in the left half we will divide the subarray into left half into two halves. So the time complexity in binary search is log n, whereas in linear search it is n, and n is always greater than log n. But the space complexity of binary search is less as compared to linear search, because the number of variables in binary search, just like mid, high, low, they are more. So the space complexity of binary search is more as compared to linear search. So this is an example of time space trade-off. Next topic is abstract data type. Next topic is abstract data type. So abstract data type is nothing but set of data. We know what is to be done and we don't know how it is to be done. We know how to drive a car, but we don't know what is the internal implementation detail of the car. We know gear, clutch, brake, race, everything, but we don't know about the internal implementation of the car. So that is called, this is an example of abstract data type. So we know what a specific data type can do. We know what a data type can do, but how it actually does is not known. What is the example of abstract data type? Just like we know stack is last in first out, but whatever element is inserted in the last, that will be pop out as the first element. but we don't know how it is implemented, whether the stack is implemented as an array or whether the stack is implemented as a linked list. We don't know about this. Just like queue, we know first in, first out. We know the property of first in, first out, but we don't know how it is implemented, whether it is implemented through linked list or whether it is implemented through array. So when we don't know the internal implementation detail, but we know what the basic model and what the data type can do, what exactly it will do, that is to be known to us. That is called as abstract data type. So basically the model of abstract data type is, we have application program with us, and that application program is interface with public function, private function. We have some public function, we have some private function, we have data structure just like array, linked list. So this particular part is abstract to us. This particular part is abstract to us. The public functions, the private functions, and the data structure involved. What is the dynamic memory involved? So that is hidden part. So this part is hidden to us. This is hidden to us. So we also know about the application program, what exactly this application program will do, what exactly it will do. So that is known to us. So this is about the abstract data type. So when we are writing an ADT for anything, let's suppose I need to write ADT for stack. So I am writing ADT for stack. I need to write the ADT for stack. So first of all, we need to write the instance. What are the instances? Instances is nothing but just like stack is a collection of elements one after the other. Stack is a collection of elements one after the other. Next comes the precondition. What is the precondition of stack? The precondition of stack is last in, first out. That last inserted element would be pop out first. Now we need to specify what are the operations that are associated with stack. Operations are, you can easily know that push is one operation, pop is operation, display is another operation. Push, pop and display. These are three operations that are associated with stack. So push, insert the element on top of the stack. This is insert element. Insert the element on the top of the stack. Pop element, delete element from top position. That is called as pop operation. When we are popping the elements one after the other from the top, that is what we can easily see that the stack scenario would be like this only. First A element is inserted, then B element is inserted, then C element is inserted one after the other. And when we are talking about the pop operation, first C will be popped, then B will be popped, and then A will be popped, because this is top. And when we pop C, the top equal to top minus 1. In that case, top would be top minus 1. Next is the display. Display function will display the content of the stack. It will display this content of the stack from the top position. It will only display the content of the stack from the top position. From the top position only. So this is how we can easily write the ADT for stack, ADT for queue, ADT for set, because we know what exactly are the operations associated with what are the preconditions, what are the instances, and how the operations are performed. But we don't know the internal implementation detail. That's why this is called as abstract data type. That's it. In the next lecture, we will talk about a singly linked list. Thank you.